Hi. This deck of slides will cover a couple of example calculations based on concepts that we've learned on AC power and on transformers. So let's proceed. So here are pictures of transformers. On the left here is a distribution transformer, which we commonly see mounted on street poles. On the middle is a power transformer that we have in substations. Some of you may have seen this, but it's not as common as these smaller distribution transformers there. On the right is a simplified diagram on what is inside the transformer. Basic components include a conductor forming winding one. That's a conductor that's wound around the core. Another conductor forming winding two. And these two windings are wound on a common core to couple the magnetic flux between them. So to achieve voltage transformation, winding one and winding two should have different number of turns. So that's a key parameter here. N1 for the number of turns in this winding one, N2 for the number of turns in winding two. A symbol for transformer with important parameters is shown here on the left. We have winding one with N1 turns and winding two with N2 turns. We do have voltage V1 here across winding one, current I1 flowing through winding one, voltage 2 across winding 2, I2 flowing through winding 2 as well. Because the magnetic flux is coupled between the two windings and voltage induced to changes in the common magnetic field. If you remember Faraday's law, the ratio of the voltages is equal to the turns ratio. So this is what we have. V1 over V2 is equal to N1 over N2. If we assume that we have an ideal transformer here where no losses is incurred, the apparent power in the primary winding, that's V1 I1, is equal to the apparent power V2 I2 in the second winding. We can do the maths here. We can rearrange such that V1 over V2 is equal to I2 over I1. This one is the ratio for the currents. Hence, we can get the ratio for the currents I2 over I1 is equal to N1 over N2. Notice the difference between this one and this one here. That's V1 over V2 equal to N1 over N2. That's I2 over I1 equal to N1 over N2. Okay, let's do some examples. Number one, some Filipino households, you might have this at home as well, have a 220 volt or 110 volt transformer that are used to, with appliances that are rated 110 volts. So if you have an appliance that was bought overseas, it's rated 110 volts, then you need a transformer to be able to use that. So the first question is, what's the turns ratio? High to low. So it's basically, you need a 220 to 110 transformer. So that's 220 to 110 is equal to 2:1. Which side is connected to the supply and which side is connected to the load? So the supply side is the 220 volts in our outlet. The load side is our appliances. Okay, so 220 volts of the transformer to be connected to the supply side. The 120 side, the 120 volt side of the transformer will be connected to our appliance. If a transformer is used with an appliance that draws 5 amperes, how much current flows through the other side? So 5 amperes is on the appliance side, which is on the low side. We can use it I2 here as 5 amperes. But V1 over V2 there, V1 is 220, V2 is I110. Therefore, I1 will have 2.5 amperes. Take note that I2 is in the low side, that's the low voltage side. I1 is the high side, that's the high voltage side. But the currents are opposite. We have higher current in the low side, lower current on the high side. What's the volt ampere rating of the transformer? So we can solve it two ways. We can solve this on the high side, which is equal to 220 volts times 2.5 amperes. That's 550 volt amperes. Or we can compute it on the low side. That's 110 volts times 2.5 amperes. Sorry, times 5 amperes. That's 550 volt ampere. Let me say that again. So either high side, 220 times 2.5 amperes, that's 550. Or low side, 110 times 5 amperes, that's 550 volt ampere as well. So you can do it either way. Item number 2. Suppose you have a distribution transformer supplying power to a small business. The rating of the transformer is 13.2 kilovolts to 220 volts. That's the high side, that's the low side. And the rating in terms of power is 25 kilovolt amperes per kVA. The question is, how much load current can be utilized by the business? When you say load current, then that must be on the low side. So the load, the appliance earlier are both on the low side. So what will be the maximum current here? That's 25 kVA divided by 220 volts. That will give us 113.64 amperes. So the key here is we should realize that the customer, small business, is connected on the low side of the transformer. That's the utilization side. Item 3, a generator step-up transformer is rated 13.8 kV to 230 kV. Again, these are both high voltages or large voltages, but this one, 230 is the high side, this one is the low side. The generator is rated 50 MVA, so that's 50 million volt ampere. So the question is, at full load condition, when the generator is fully loaded, when the transformer is fully loaded, how much current is expected at either side of the transformer? So we start on the low side, that's 50 MVA there at 13.8 kV. The current should be 50 MVA divided by 13.8 kV. That should be 3.62 kiloamperes. On the high side, that should be 50 MVA divided by 230 kV. The current turns out to be 217 amperes. Take note that we have the low side here, higher current, high side here, lower current. And that's one of the main reasons why we use transformers. We step up the voltage so that the current will be scaled down. I hope this part is clear. If you have questions on this, feel free to discuss via forums. Here's another example here. We read through this first. Appliance 1 at home is operating at 220 volts. It has an impedance of 100 plus J50 ohm. Calculate the current and power absorbed by this appliance. Item 2 says that there's a second appliance. Appliance 2 at home is operating at 110 volts, has an impedance of 100 plus J50 ohms. Apparently, the impedances are equivalent. Calculate the current and power absorbed by this second appliance. If this appliance 2 will be used in a 220 volt supply, and it's rated 110 volts, then we need a transformer. What should be the turns ratio of the transformer to be used? Specify the supply side and the low side. Item 3, these two appliances, together with the necessary transformer, is connected to 2 outlets of an extension cord. If the extension cord has a total impedance of 2 plus J1 ohm, calculate the power loss across the extension cord. So that's the problem. Of course, we solve this one at a time. Let's go back to appliance 1 day. So appliance 1 at home, 220 volts, impedance of 100 plus J50 ohms. So the current through it is V over Z. We know it's 220 volts. We pick this as our reference. So we assign angle 0 to it. We divide it by the impedance as the impedance at 100 plus J50. If we do the maths, we can solve it to be 1.97 angle minus 26.5 amperes. So this is the current through appliance 1 or drawn by appliance 1. For us to solve for the power absorbed by this appliance, if it wasn't specified, power refers to the real power, not the reactive power, not the apparent power yet. So power, real power P here. And we learned before that P is equal to I squared R. So you grab the magnitude of I, square that, you multiply it by the resistance, not by the impedance, but just the resistance component, the R. That's I squared R. You get your real power P here. That's 388.09 watts. Take note that the real power per se is a scalar quantity. The current is a phasor quantity, a complex number, but P is a scalar quantity in units of watts. I hope this part is clear. Again, if you have questions, we can discuss via forums. Let's look at appliance number 2. So we're again asked to solve for the current and the power absorbed by this appliance. Again, voltage is 110 volts. Again, set this as reference, angle 0, divided by the impedance, which is similar to the first one. And this will be the current, 0.98 angle minus 26.5 degrees. Power drawn by the second appliance is again I squared times R. That's 96.40 watts. So that's the power drawn by appliance 2. But wait, we were told that we need to use a transformer for that. So that if we have a transformer, the transformer will have a ratio of 110 to 220. 110 on the low side, appliance side, 220 on the high side, the outlet side. So that's the turns ratio multiplied by the current drawn by appliance 2. That's a scalar quantity. You multiply it by a complex number here, you get a complex number. The angle stays the same, but the current magnitude is now 0.49 amperes. Hopefully that makes sense. If we now have higher voltage on the high side of the transformer, the current should be lower than the original. If the turns ratio is 2:1, then current will be halved for the high side. For item 3, we were told that these two appliances, with the transformer, of course, are connected to two outlets of an extension cord. If the extension cord has a total impedance of 2 plus J1 ohm, calculate the power loss across the extension cord. So how much current will really flow through the extension cord? Basically, it's the sum of I1 and I2. I1, we computed earlier, is 1.97, angle minus 26.5 degrees. I2 is 0.49. Take note, this one is on the high side of the transformer. That's the one that's going to be connected to the outlet. So that's 0.49 angle minus 26.5. We add them together, we get this current through the cord. And finally, the power loss across the cord is again I squared R. That's the current, we square that. Resistance of the cord is 2 ohms. That's 2 I squared. That's 12.1 watts. So we say that for this example, we have a 12.1 watt loss across the extension cord. This example involves high power, large power devices such as generators and large transformers. So the description is the voltage at the terminal of an AC generator is measured to be 12 kilovolts per phase. It's line to neutral. It is scheduled to deliver 35 megawatts of real power and 30 megavars of reactive power per phase. The first item is calculate the current at the terminal of the generator. Second, if a generator step-up transformer is used to step up the voltage to 230 kilovolts, calculate the current at the high side of the transformer. Third, if the transmission line has a resistance of 1 ohm, calculate the losses for a case without a transformer and with transformer. So let's proceed. So as before, our key equation is shown here. The current is equal to the P minus JQ over V conjugate. That actually came from the expression for S conjugate here, which is equal to V conjugate I equal to pi P minus JQ. For the first one, we don't have a transformer. So the current is 35 megavar minus J, 35 megawatts, sorry, minus J 30 megavar divided by 12 kilovolts. Again, we assume our voltage to be our reference, this at an angle 0. The current turns out to be 3.8 kiloamperes, angle minus 41 degrees. We're also asked to calculate the losses. With this current here, losses through the line is equal to I squared times the resistance. So that's 3.8 kiloamperes squared times 1. That's 14.4 megawatts, which is quite significant. So we have 35 megawatts of power, but the losses turn out to be 14.4 megawatts. That's a lot of losses. So the second case is we have a transformer and we transform the voltage to 230 kilovolts. So the current this time is 35 megawatts minus J 30 megavar divided by 230 kilovolts. And the current will be 200 angle minus 41 degrees in amperes. To calculate the losses, that will be I squared R again. That's 200 amperes squared times 1. That will give us 40 kilowatts. So 40 kilowatts, notice, is a huge loss reduction. So we emphasize in this illustration that when we use a transformer to transform the voltage from 12 kilovolts to 230 kilovolts, we were able to reduce the losses significantly. The second set of problems here is pretty much similar to the first one, except that the megavar produced by the generator is now 0. So instead of producing 30 megavars earlier, we now reduce that to 0 megavar. And as before, we calculate the current, we use a transformer, and then we calculate the losses as well. So the same formula holds. The same equation actually is applied. So I is equal to 35 megawatts minus J megavar, 0 megavar, divided by 12 kilovolts, angle 0 as reference. We have the current 2.9 kiloamperes at an angle 0. Notice we have angle 0 here. At 0 megavar, the voltage and the currents are now in phase. We have a purely resistive system here. The losses, as before, is I squared times the resistance. That's 2.9 kiloamperes squared times 1. That would be 8.4 megawatts. Notice that this is a little bit lower than the 14.4 megawatts that we solved earlier. If we have a transformer, again, we increase the voltage to 230 kilovolts. So the current is now 35 megawatts minus J 0 megavar divided by 230 kilovolts. That results to 152 amperes here. And the losses this time is 152 squared times 1 equal to 23.1 kilowatts. Again, compared to the previous case, P losses were reduced further when the reactive power dropped to 0. So what we have learned in these two illustrations is that using a transformer, we can reduce the losses. If there's a way to have the reactive power reduced to 0, that can reduce the losses as well. So that's our third example. And that's it for now. Again, if you have questions on this, feel free to discuss via any of the forums available. Thank you.